So now we're going to be looking at the QT interval, which is the final part of the analysis of the 12-lead ECG. Now, the QT interval is the time taken for all of ventricular electrical activity. So, it's the time from the beginning of ventricular depolarization to the end of ventricular repolarization. So essentially, when looking at the QT, we are interested in the length or the time. So what is the normal QT? So in men, it is a little shorter than in women. So in men, it is 440 milliseconds, and in women, it is 460 milliseconds. So on the ECG, that would be the same as 0.44 and 0.46. Okay. All right. So there's an important concept that I'd like to explain. So the QT interval varies with heart rate. So let me explain. So we already explained that the QT interval is the period from depolarization to repolarization of the ventricle. Now, if your heart rate is slow, let's say 50 beats per minute, your ventricle has more time to depolarize and then to relax, which would be to repolarize before it can go again. Right? So as a longer QT interval would not be surprising at a slower heart rate, right? However, as the heart rate gets faster, your heart needs to conduct what it's doing, so to speak, at a more rapid rate, okay, to keep up with its normal function. So therefore, the time taken to depolarize and repolarize needs to be shortened. So let us say at 150 beats per minute. So the QT interval, right, has to be much shorter when the heart rate is faster. Therefore, while we do measure the absolute QT interval, we know that it's normal for the QT to vary with heart rate, and therefore we also have to calculate a corrected QT interval that will appropriately take into consideration the patient's heart rate. So shortly, I will show you how to measure the QT interval, and I will also show you the formula for calculating the corrected QT interval. So another question you might ask is, why is the QT interval important? Okay, so this is the explanation. Essentially, when the ventricles are repolarizing, this is a very vulnerable electrical period. If a new impulse happens prematurely, such as from an ectopic site, while the ventricles are repolarizing, this can be an ideal situation to set up a dysrhythmia or an abnormal electrical rhythm, especially ventricular tachycardia or ventricular fibrillation. So during this vulnerable period, if there is an abnormal electrical impulse, right, it can result in a tachycardia, which can be fatal, right? So the longer the QT interval, the more susceptible a patient might be to these ectopic foci of electrical activity, because in a given cardiac cycle, the heart is spending more time in repolarization, essentially. So when speaking about ventricular repolarization, you have something called the absolute refractory period and the relative refractory period. So if an abnormal impulse occurs here during the relative refractory period, right, the ventricles are in a state in which they can no longer during this period conduct an impulse, right? So if we get an abnormal impulse occurring right here, then it is unlikely to cause a tachycardia. In fact, it just won't conduct at all. But in this relative refractory period, what we have is that some of the ventricle may still be depolarized and some of the ventricle has started to repolarize. So this part of the ventricle can conduct an electrical impulse, and this may result in a situation where it conducts, and by the time it gets to this part of the ventricle, it has started to repolarize as well, and so the impulse can conduct and it will go in that fashion, forming an electrical circuit where it goes round and round and round, resulting in a tachycardia. So in summary, what I want to get across is that if impulses occur during this relative refractory period, right, ectopic ventricular impulses, it can result in a life-threatening tachycardia. So therefore you can see how if my QT interval is longer, there's more time and a greater chance that an impulse might fall during this relative refractory period. So in later videos I will go into more detail about possible causes of a prolonged QT interval. So let's now talk about how to measure the QT interval. So here we have a normal ECG, and we'll use this as practice to measure the QT interval. So let's pick a lead. You can pick V3 and let's zoom in. So we said the QT is from the beginning of ventricular activity, which would be the beginning of the QRS complex, to the end of ventricular activity, or the end of the T wave. So we're going to say it's about right there, right? And so this is the QT, right? So let's just check that out. So this one of these is 0.04, 0.04, right? 0.08, 0.12, 0.16, 0.20, 0.24, 0.28, 0.32, 0.36, and then maybe a half, 0.38. So this person's QT is about 0.38 or 380 milliseconds. So it's not prolonged. In fact, I would say it's probably more about 400 or 0.4. So let's look at another lead. So this is, so using lead 2, this is lead 2. So about right here, it is, so this would be 0.2, right? And then, okay, so 0.2, 0.24, 0.24, 0.28, 0.32, 0.36 and a half. So I guess it was correct, about 0.38. Okay, so this is normal. So short QT is less than 360 in males, and less than 370 in females. So this is a normal QT. So now let us calculate the corrected QT. So to do so, we'll use Bazet's formula. So there are, right, pardon my spelling. So Bazet's formula. So there are other formulas, but this is the most common, and I think it's sufficient to know one formula. So Bazet's formula is the measured QT over the square root of the RR. So let's take that on. So we already measured this patient's QT, right, which is 0.38. Okay, so what is the RR? So that's from here to here. All right, so let's zoom in. It would be, okay, from here to here is 0.2, 0.4, 0.6, 0.8, and then we're going to add a tiny box here, so that's 0.04, and another one here, 0.04. So I would say this is about 0.88. Okay, you can always slow it down if I'm going a little too fast. So what we're saying is, using Bazet's formula, this patient's corrected QT will be 0.38 over the square root of 0.88. So now, using the calculator, the square root, okay, there we go, I figured it out. So the square root of 0.88 okay is 0.938. okay, let's write that down. So we would divide 0.38 by 0.938, and that would be 0.405 or 405 milliseconds. So that's a normal corrected QT. So let's do a few other examples, or at least one other example. Okay, so let's measure this QT interval. Let's use an easy lead, like, okay, let's use lead 3, and let's zoom in. Alright, so our QT interval would be from here to here. Alright, so starting at 0, this would be 0.2, 0.4, 0.6. Okay, so this would be 0.8, and you minus 0.04 from that, so that would be 0.76 if my math is correct. Okay, so our QT is 0.76 or 760 milliseconds, which is really fast. But remember, just looking at this rhythm is pretty bradycardic. So let's do the corrected QT, right? And we'll see if it's really prolonged or it's just a reflection of the bradycardia. So the corrected QT is equal to the QT over the square root of the RR, right? We already did the measured QT, which is 760. Let's measure the RR. So we're gonna go from here to here. All right, so let's zoom in. This is 0.2, 0.4, 0.6, 0.8, 1, Sorry about that. Hold on. Okay, so this will be 1, 1.2, 1.4, 1.6, 0.8, 2.0, about 2.2. So therefore we're saying, right, the corrected QT would be equal to 0.760 over the square root of 2.2. So let's put that into the calculator. So the square root of 2.2 is 1.483. So 0.760 divided by 1.483. 0.760 divided by 1.483. Okay, so that gives me a QT of 0.512. So the QT is indeed prolonged. All right. So there's one last trick that I would like to use, or there's one trick that I'd like to teach you that you can use to estimate whether or not a QT or the QT is prolonged or normal just by looking at the ECG. All right. So it works well with rhythms of normal rate and tachycardias as compared to bradycardias, right? Or rather, perhaps I should scratch that. It works best with rhythms that are of a normal rate, so 60 to 100. Okay, so essentially what the trick is, if the QT, right, which is here, if the QT is less than half the RR interval, then the QT is not prolonged. Right? So we can see just by looking at this, the QT looks like at least a little bit less than the RR interval. So this QT is going to be normal for sure. Alright, so you're just estimating. Now I'm going to show you a QT that's prolonged. Okay, so let's look at this ECG. And let's pick a lead to look at the QT. So we're going to pick a lead that it's very readily observed, and we're going to pick V5. So the QT would be from here to about here, and the RR is from there to there, and this would be half the RR. So we can see that the QT is quite long compared to the RR, and so without even doing a measurement, we can estimate that this patient has a prolonged QT. Okay, let's look at another ECG, another example. So let's pick a lead where it's readily observed or easily observed. Okay, let's look at lead V2, and the QT would start here and end somewhere about here, and this is the RR, and this is about half of it. So just by looking at this, we can see that this distance, right, is a bit more than half the RR, and therefore just by looking at this ECG, we can tell that the QT is grossly prolonged. Of course, we could do the corrected QT and give an exact measurement for that.